Hello students, in today's session you will be learning about the basics and the principle of infrared spectroscopy. So let's begin. Purpose of IR spectroscopy. Firstly, this technique is used for the analysis of inorganic and organic compounds. Secondly, this technique is used for the characterization of solid, liquid, and gas samples. Thirdly, with the help of this technique, vibrational changes in the bonds are produced, which then helps in providing the information about the functional groups and the bonds present in the molecule. Infrared spectroscopy involves the interaction between IR, infrared radiations, and the matter, and the part of spectrum comprising IR radiations is further divided into three different regions. The first region is near IR region, and the wavelength range for this region is 0.8 to 2.5 micrometer, and we represent the wavelength with the sign lambda. The wave number range for this region is 12,500 to 4,000 per centimeter, and we represent the wave number with the sign nu bar. Second comes the middle IR region. The wavelength range for this region is 2.5 to 25 micrometer, and the wave number range is 4,000 to 400 per centimeter. Third comes the far IR region. The wavelength range for this region is 25 to 1000 micrometer, and the wave number range is from 400 to 10 per centimeter. Now, out of these three regions, it is this middle IR region which is generally used for spectroscopic analysis. The reason is that the organic molecules rarely show any absorption in near IR and the far IR region. And this wavelength range, or I can say the wave number range for this middle IR region, can vary from instrument to instrument. The main thing which I would like to add on here is that the wave number is inversely proportional to wavelength, or we can say lambda. And using this equation or the expression, you can easily carry out all the conversions which are shown here in the table. Let me do one for you. So for example, the wavelength is 0.8 micrometers. So in first step, we will convert this wavelength from micrometers to centimeter by doing it times with 10 to the negative 4. So now we have got the wavelength in centimeters. Now using above expression, we can express this wavelength in terms of wave number. So 1 by 0.8 times 10 to the negative 4. So as we are doing the inverse, so we will get here centimeter inverse. And on doing the calculations, you will get 12,500 per centimeter. So this expression can help you to carry out all the conversions which are shown here. So now let us learn what happens on interaction between infrared radiations and the matter. So in our previous session, I have already told you that either the absorption or emission of electromagnetic radiations can take place. Here, in this spectroscopic technique, the absorption of IR radiation will take place. A change will be noticed in the atom or the molecule. And the change noticed here will be in the form of molecular vibrations. and which will then lead to the formation of absorption bands. The absorption bands, we can also say that they look like the upside down peaks. Step by step, I will introduce you more with the absorption bands. So now let us learn why the molecular vibrations are noticed on the interaction, why not the electronic transition. So here in case 1, you can see that particle in the ground state is showing the vibrational transition by absorbing the IR radiation, whose energy is equal to the energy difference between these two levels. And in case 2, the particle in the ground state is showing the electronic transitions by absorbing the UV radiations, whose energy is equal to the energy difference between these two levels. Now, UV radiations, being higher in energy, can carry out high energetic electronic transitions, and on the contrary, IR radiations, being lower in energy, can only carry out low energy vibrational transition. So, depending upon the energy of electromagnetic radiations, a change is noticed within the molecule on the interaction. Molecular vibrations. Periodic motion of the atoms of a molecule relative to each other, such that the center of mass of the molecule remains unchanged. And it is considered that the covalent bonds in the molecules are not rigid, but they are more like stiff springs. So here, the bond between oxygen and hydrogen is represented with this spring, and the two atoms are represented with the balls, the blue ball and the green ball. And as you can see, the spring is continuously going under compression and extension. So this constitutes the basis of molecular vibrations. Types of molecular vibrations. Molecular vibrations can be classified into two types. First, we have stretching vibrations, and second, we have bending vibrations. Stretching vibrations are further classified into two types: symmetrical stretching vibrations and asymmetrical stretching vibrations. Bending vibrations are further classified into two types. We have in-plane bending vibrations, we have out-plane bending vibrations. In in-plane bending vibrations, we have scissoring and rocking, and in out-plane bending vibrations, we have wagging and twisting. Let us learn more about them in detail, one by one. Stretching vibrations. These vibrations are defined as periodic back and forth movement of the atoms connected to the central atom along their covalent bond axis. And during these vibrations, changes in bond length are noticed, whereas the bond axis remains the same. Stretching vibrations are of two types: symmetric stretching, asymmetric stretching. In symmetric stretching, two atoms shown by blue balls can either move towards the central atom shown by green ball, or they can move away from the central atom. In other words, we can say that the bonds are either getting stretched or compressed. Asymmetric stretching vibrations involves the movement of one of the atom towards the central atom, whereas the other moves away from the central atom. Or in other words, we can say that one of the bond is getting stretched and the other bond is getting compressed. So these two changes which are taking place, you can clearly see here. In plane bending vibrations. As the name denotes, in these vibrations, both the atoms are going to vibrate in plane with respect to the central atom. During these vibrations, changes in the bond angles as well as the bond axis are noticed. In-plane bending vibrations are of two types, scissoring and rocking. In scissoring vibrations, the two atoms shown by the blue balls here can either move towards each other or they can move away from each other. Scissoring vibrations forms the same case like when we use scissors to cut the paper. Rocking vibrations. In these vibrations, the two atoms can move in same direction with respect to the central atom. So when I say same direction, it means both of them are either moving towards right side or both the atoms are moving towards left side. Outplane bending vibrations. As the name denotes, in these vibrations, both the atoms are going to vibrate out of plane with respect to the central atom. These vibrations are of two types, wagging and twisting. In wagging, both the atoms are going to move either above the plane or below the plane with respect to the central atom. In twisting vibrations, one of the atom is going to vibrate above the plane and the other one is going to move below the plane with respect to the central atom. Now, as we have learned about vibrations, a question can be formed that out of stretching vibrations and bending vibrations, which one occurs at higher energy or higher wave number? The answer to this question is that stretching vibrations are found to occur at higher wave numbers in comparison to the bending vibrations because it's quite harder to stretch the bond in comparison to bend it. Principle of IR spectroscopy. Step 1. Energy in the form of infrared radiations is applied to the sample molecule. Step 2. It will cause vibrations in the atoms of the molecule. Step 3. When applied IR frequency equals the natural frequency of vibration, then absorption will take place and an absorption band will be observed. Note here that different bonds absorb IR radiations corresponding to different wave numbers. Therefore, they will show characteristic absorption bands in the spectrum. For example, if within the molecule we have got carbon-hydrogen bond, oxygen-hydrogen bond, or I can say carbon doubly bonded to oxygen or carbon single bond oxygen. So all these bonds will show their separate characteristic absorption bands in the spectrum, and those absorption bands will correspond to different wave numbers. Let me explain you the principle of IR spectroscopy with a simple example. So as you can see here, we have got the source, or I can say the light source, which can emit IR radiations of varying wave numbers. Next to it, we have the sample molecule, which is formaldehyde, and formaldehyde contains carbonyl group, which I have highlighted here, and it's shown by carbon doubly bonded to oxygen. This carbonyl group can show two types of vibrations, like it can stretch at the wave number 5 per centimeter, and it can show wagging vibrations at wave number 3 per centimeter. So first case, when our source will emit light radiations corresponding to wave number 1 per centimeter, and these radiations are then made to interact with this carbonyl group, we have to think what will happen now. So, what do you think? Will there be any absorption taking place or not? No, there will be no absorption which will happen corresponding to this wave number, because the wave number of IR radiation doesn't equal the wave number of any of the vibrations. It's neither equal to the stretching vibrations, neither equals to the wagging vibrations. So no absorption will happen, and as a result, whole amount of the light will pass through the molecule and will reach the detector. And detector will say, yes, I have detected this radiation. Let us talk about case second and third, where we have the IR radiations corresponding to wave number 3 per centimeter and 5 per centimeter. So when these two radiations turn by turn are made to interact with this carbonyl group, so we can see that these two radiations are matching with this wave number. So now, as the wave number of IR radiation equals the wave number for the stretching and the wagging vibrations, so in this case, absorption will take place. So absorption will happen and detector will not be able to detect any of the light. So here, what we will conclude that there must be certain kind of absorption which will have taken place. So after the detector, everything goes on to the recorder. So as the name denotes, recorder means which is going to record something. So here the recorder is recording the data in the form of spectrum, which we call as IR spectrum. So this spectrum is basically a graph which is plotted between percentage transmittance taken along y-axis and the wave number taken along the x-axis. So if I talk about case 1, where we have the radiations corresponding to wave number 1 per centimeter, now we know the complete light was passed through the molecule. So here I have shown a mark corresponding to 100% transmittance, means nothing was absorbed by the molecule. Similar will be the case corresponding to wave number 2 per centimeter, as it doesn't match with any of the stretching and the wagging vibrations wave number. So there is again 100% transmission, or the light passed completely through the molecule and reaches the detector. In case second, corresponding to wave number 3 per centimeter, and in case third, corresponding to case 5 per centimeter, we know that absorption took place. Now in this case, it's not like the case that 100% of the light will be absorbed by the carbonyl group. So as you can see here, corresponding to wave number 3 per centimeter, I have shown that 20% of the light is getting transmitted and 80% of it is absorbed by the carbonyl group. Similarly, for radiations corresponding to wave number 5 per centimeter, it's shown here in the graph that 40% of the light is getting transmitted, means passed through the molecule, and 60% of it is getting absorbed. And corresponding to wave number 4 per centimeter, as it doesn't match with any of the stretching and the wagging vibrations, so no absorption happens over here too. So it's shown 100% transmission. So let's see what will happen if we will join all these points together. Now you can notice that upside down peaks are getting formed, or the dips are shown in the graph. So I have already told you at the very start that the upside down peaks are known as absorption bands. The word absorption is used because corresponding to these two wave numbers or these 2 points, absorption is shown by the molecule. So that's why we are calling them as absorption bands, or we can say upside down peaks. And wherever the absorption will take place, a dip will be noticed in the curve. Note one thing here, that the wave numbers which I have shown for stretching and wagging vibrations, I have taken them too small to make the things clear to you in the simple way. Otherwise, in actual, they occur at higher wave numbers, or the stretching and wagging vibrations are found to occur at higher wave numbers. So kindly keep that thing in mind. So I hope with this small example, the principle of IR spectroscopy will be clear to you. So let's revise what we have discussed till now. When applied IR frequency equals the natural frequency of vibration, absorption of IR takes place and an absorption band is observed. Molecules are excited to higher state vibrational energy level from the ground state when absorption takes place. When a compound is exposed to IR radiation, it selectively absorbs the radiations, resulting in vibration of the molecules of the compound, giving rise to closely packed absorption bands, which is what was shown in the spectrum. Absorption bands correspond to characteristic bonds and functional groups present in a chemical substance. We will be talking about all these things in detail in our next session. So let's brainstorm and check what you have learned till now. Question 1. Who requires less energy to vibrate? Bending or stretching vibrations? Question 2. Name one in-plane and one out-plane bending vibration. Question 3. Convert 20 micrometer to per centimeter. Question 4. When will absorption bands be noticed in IR spectroscopy? I hope you will be able to solve these questions by yourself. And if you still feel any kind of difficulty, you can click on the link in the below box. Till then, keep watching, keep learning.